Welcome back, everyone. So in this video, we're going to talk about waves, right? What is a wave? How do you classify a wave? How do you tell, or how do you distinguish one wave from another wave? What are the different types of waves? Things like that is all the sorts of stuff we're going to get to in this video. In another video, we'll go into different things that waves can do, more properties of waves, but this one's going to be more of just a definition of a wave, different types of waves, how to quantify different parts of wave, things like that. Anywho, let's get started. All right, so waves, right? So first off, what is a wave? Well, a wave is a series of pulses. Okay, then what's a pulse? Well, a pulse is a single disturbance in a medium. All right, so then what's a medium? Well, a medium is just the thing that the wave travels through. All right, so let's kind of talk about these three things in a little bit. So a medium could be literally anything that a wave travels through. With me speaking, it's the air, right? The sound waves are traveling through the air into my phone's microphone, which then get converted into what you are listening to now, on the other end, right? Strings, for example, right? If you play or listen to music that is played on a stringed instrument, right? That wave travels through the string, which then vibrates the air, so then it becomes also air. Water, literally anything can be a medium, okay? Now, a pulse versus a wave, right? So let's see this. That single clap is just a pulse, right? You picked it up with your ears, and then it was over. Now, if I was to make a wave, I'm doing it over and over and over again, okay? So that's sort of the difference between a pulse and a wave. All right, now, we mostly talk about two different types of waves, okay? So let's go through each of those types of waves and their key similarities and their key differences. All right, so the first type of wave we're going to talk about here is a longitudinal wave. Longitudinal wave. Let's make sure it's spelled right. Now, what's a longitudinal wave? Longitudinal wave is when the particles in that medium vibrate parallel to the wave's motion. Right? So the particles vibrate parallel to that wave's motion. Right? So let's see what that looks like. Okay? Now, for this particular diagram, our particles are going to be represented by vertical lines. Okay? So let me just draw that real quick. Okay. Now, this might not look like much at first glance, but let's take a look. If you notice, here and here, the lines are closer together than, say, here or here. Okay, that's because what's happening is the particles are vibrating back and forth, right? It's a this kind of motion. Okay. Now, we say it travels parallel to the wave's motion because we can say that the wave is traveling that way. Okay, so as the wave is traveling through air, the particles are moving back and forth, right? Since they're both horizontal, we say that's parallel. It's a horizontal wave. Think of a slinky, right? Have you ever taken a slinky, curled up the coils on one end and then let it go, and you see it kind of transfer down? That's a longitudinal wave. Now, beyond just a slinky, what are some examples of longitudinal waves in real life? Well, one of those would be sound, and the other would be, if you can think back to your wave theory, or your earth science class, that would be a P wave. Okay. Sound waves and P waves are longitudinal, right? So sound, what's happening is, as you speak, you're creating differences in pressure in the air. As that difference in pressure propagates throughout the air, that wave travels through the air, can be picked up by a microphone or someone's ears, and then that gets interpreted into what you hear as sound. Okay? A P wave, again, if you remember from earth science, is this sort of like pressure wave that travels through the crust and is detected by seismographs. Okay? Great. So that's a longitudinal wave. Now, the other kind of wave that we talk about here is a transverse wave. Okay, a transverse wave. Now, the definition of a transverse wave is the particles vibrate perpendicular to the wave's motion. Okay, the particles vibrate perpendicular to the wave's motion. All right, so how does that look? Let's draw a picture. So that would look sort of like this. Okay, so as the wave travels this way, the particles are vibrating up and down, right? You have this kind of motion, this up and down sort of motion. Right, so that is a transverse wave. Now, what are some examples of transverse waves in real life? Okay, well, we have light, and again, talking about seismic waves, we have those S waves. So light waves and S waves are longitudinal, or sorry, transverse. They're transverse. Okay, alrighty. Now, moving on. There are another set of ways that we can classify waves. Okay, so we have longitudinal and transverse, but we can also have something called mechanical waves versus electromagnetic. Now, all light waves are electromagnetic, right? If you remember the electromagnetic spectrum. Mechanical waves is anything that needs a physical medium to travel through. So it has to have something physical to travel through. So mechanical waves cannot travel in a vacuum like space, for example, right? Mechanical waves would be sound, something on a string, anything like that. Light waves, being electromagnetic waves, we know they can travel through near vacuums, because how else would the light get from the sun to Earth, right? There's not much in that space, right? It's nearly a vacuum, right? So we say that electromagnetic waves can travel through a vacuum, but mechanical waves cannot, okay? All right, now let's talk about different characteristics of waves. To do that, what I'm going to do is I'm going to draw a transverse wave on my whiteboard here. Now, everything that we talk about for this particular section, this characteristic section, can be applied to longitudinal waves. It's just easier to draw and label a transverse wave. Right, so to start, I'm going to draw a horizontal line through my wave. Now, I'm not a very good drawer, so pretend that this is a perfect kind of bisection of the wave. This horizontal line represents the equilibrium line, which means if there was no wave traveling on it, it would just be nice and flat, right? So think of a guitar string that hasn't been plucked yet, or air that doesn't have sound traveling through it, or a pool that hasn't had any ripples going through it, or anything like that, right? That's what that represents, the equilibrium line. Right? Now, let's go through and label different parts of this wave here. Okay, this top part, sort of the upper bump, we call a crest. Call it a crest. Okay, this bottom part we call a trough. Okay, T-R-O-U-G-H. Okay, crest up top, trough on the bottom. In a longitudinal wave, the crest would be considered to be where the particles are closest together, and the trough would be where they're furthest apart. Okay, excellent. Now, the next one is a wavelength. Okay, and a wavelength would look something like this. Okay, so let's kind of break down what I drew here. So I started at a crest, and I went directly to the next crest. So the definition of a wavelength is the distance, so this measurement here, from one point on a wave to the next identical point. Okay, I could measure a wavelength this way, from crest to crest. I could go trough to trough. I can pick this spot on the equilibrium line, and I can bring it to the next identical spot. Okay, the reason I can't go here is because if I were to trace this, right here I'm going down, scoot up. Now here I'm going up, but as I come back, I'm going down again. So these two are identical points. The idea is it has to be the same kind of point, right? So crest to crest, trough to trough, point here to point here, right? I can go from here to here, whatever, right? That is your wavelength. This symbol here, that's called a lambda, right? It's responsible for the Greek oo sound, right? That's your lambda, right? That represents wavelength. All right, so those are two key ones. Just in the interest of space on my board here, okay? I'm going to kind of erase some of this stuff just so I can make it less confusing. Now, something else to keep in mind is waves have the same types of properties or characteristics as periodic motion, right? There's an amplitude, there's a period, and there's a frequency. So amplitude I can draw. That one's easy, right? If you remember, the definition of amplitude is the distance from equilibrium, that's why I drew this line, to its maximum displacement, right? Amplitude is the max displacement from equilibrium. So from here to here. I can also go down. I can also make it from equilibrium to the trough. Doesn't matter, as long as you're measuring from equilibrium to a max displacement point. Okay? Now, it has period, which if you remember is the time it takes to complete one cycle, or frequency, which is the amount of cycles it completes in 1 second. Same definition for a wave. I can't really draw that since it's based off of time and this is a spatial board, but that's how it goes there. Okay? All right. Now, the last thing we're going to get into, the last big characteristic we're going to get into here is speed of a wave. Okay? Speed of a wave, right? The equation for that is V for speed equals wavelength, that lambda, times frequency. Okay? So the speed of a wave equals lambda, your wavelength, times the frequency. We'll smudge there. Okay. Units are still meters per second because we have meters for wavelength. We have hertz, which is a 1/second for frequency. So meters times 1/second is a meter per second. Okay, and that those are the biggies. Okay, those are the big characteristics of waves that we're going to get to in this class. In the next video, like I said, we're going to talk about what can waves do? How do they behave if you have more than one wave on a medium? So on and so forth. So keep an eye out for that one. But for now, see you later.